Let us begin the next session of this chapter, which is electric dipole. In this, we will cover the following: calculating electric field when the point is on the dipole axis, when it is in the equatorial plane of the dipole axis, that is, on a plane perpendicular to the dipole axis through its center, electric field at a general point. We will also cover dipole in a uniform electric field and the magnitude of torque and work done. The electric dipole is a pair of equal and opposite charges separated by a small distance. Here, the point charges Q1 and Q2 separated by a distance 2L. The total charge of the electric dipole is obviously zero. This does not mean that the field of the electric dipole is zero. The electric field of the pair of charges Q1 and Q2 at any point in space be calculated with Coulomb's law and superposition principle. So case 1, we're going to study 3 cases. This is case 1. Derivation when the point is on the dipole axis. 2L is the distance of the 2 point charges. The midpoint of the charge Q1 and Q2 is called the center of the dipole. A test charge Q0 is placed at the point M. Now, what is the electric field at point M due to the dipole, that is due to the 2 charges? Let us see the distance from point M to charge Q1. The distance from point M to the center is, say, R. Then the distance from the point to negative Q1 charge is R plus L. Similarly, in terms of R, from positive Q2 charge to point M will be, from Q2 to M will be R minus L. We know the general formula to calculate the electric field at a point is E equals to 1 by 4 pi epsilon naught Q by R square. Using this Coulomb's law formula, we will calculate the electric field for Q1. Here, R will be replaced by R plus L. So, the electric field due to the charge minus Q, here R will be replaced by what? R plus L. So, the electric field due to charge minus Q at the point M will be EQ equals to 1 by 4 pi epsilon naught Q R plus L whole square. For charge Q2, R will be replaced by R minus L square for the positive charge. By the principle of superposition, when we add both electric fields, the total field at M will be E equals to 1 by 4 pi epsilon naught 1 by R minus L whole square minus R 1 by R plus L whole square, keeping 1 by 4 pi epsilon naught outside the bracket. Taking LCM and mathematically solving the numerator and denominator, we will get E 1 by 4 pi epsilon naught R plus L square minus R minus L whole square divided by R square minus L square by the complete whole square. Okay. Now, when we expand these two brackets using the formula A plus B square equals to A square plus B square plus 2AB, we will open all this, solve it, then we will get E equals to Q 4 pi epsilon naught 4 RL by the denominator. Here, the magnitude of the dipole formula P equals to 2QL. To write electric field in terms of dipole moment, we can take 2 from 4 and replace 2QL with letter P, which is dipole moment. So, we get E equals to 1 by 4 pi epsilon naught 2P R square minus L square whole square. Now L is a very small, we can ignore it and cancel R with R4. Then we will be getting E equals to 1 by 4 pi epsilon naught 2p by R cube. So you can note this down. Okay, moving on. This is the case 2, derivation when electric field is on the transversal line. Here we will place a test charge at point M on the transversal line. Now, understanding the term transversal line first, we are taking a point M which is perpendicular to the dipole axis through its center. This is the dipole center point and perpendicular from that point. Okay. Calculating electric field at point M, the two equal and opposite charges Q1 and Q2 are separated by distance 2L. The distance from center of the dipole to point M is R. This distance is R. The distance of electric field will be the direction of electric field will be B to M, because both this Q2 and the charge here, the test charge, are positive, so the direction will be this side. Okay. The distance will be BP square by the Pythagoras theorem. So if you have to take out the distance, this will be BP square. So this is the distance BP. How do we take it out? Is BP square is equal to OB square plus OP square. So here OB is L and OP is R. So we can write BP square is equal to R square plus L square, or we can say the distance from B to M will be R square plus L square under root. Okay, this is by Pythagoras theorem. The general formula for electric field E is equal to, we know, 1 by 4 pi epsilon naught Q by R square. Using Coulomb's law and putting the value of distance BP, which is root R square plus L square, the electric field at point M due to charge plus Q square will be, plus Q2 will be this, 1 by 4 pi epsilon naught Q under root R square plus L square. So let us name this as E2. This is the electric field due to this charge. Okay. Now calculating electric field at M due to the negative charge minus Q. At M due to the negative charge minus Q. Here again the distance AP by the Pythagoras theorem is R square plus L square. Putting the value of distance in the Coulomb's formula, we get again 1 by 4 pi epsilon naught Q under root R square plus L square. We are going to name this E1. This is negative and the test charge is positive, so the direction will be in E1, this direction. Okay. Now EQ and E minus Q are equal in terms of magnitude, but they are not equal in terms of direction. If we actually see, both these E2 and E1 are equal in the directions, but they are equal in the terms of magnitude, but they are not equal in terms of direction. If these are not equal in direction, then we will have to divide it into two perpendicular directions. The component of E2 will be E2 sine theta and E2 cos theta. Similarly, the components for E1 will be E1 sine theta and E1 cos theta. So E1 sine theta and E2 sine theta will cancel each other as their magnitudes are same and these are in the opposite direction. Resultant electric field will be the addition of two electric fields, that are E2 cos theta plus the E2 cos theta plus the E1 cos theta. As E2 cos theta is also equal to E1 cos theta, we can write electric field will be 2 E1 cos theta. Now putting the value in the resultant, 1 4 pi epsilon naught Q R square L square. cos theta. Okay. To calculate cos theta, we know angle A, this angle A will also be theta being adjacent to the triangle APO. This triangle APO and this angle theta, so this will also become theta. So we can say cos theta equals to AO by AP, that is L by, this distance is L by under root R square plus L square. Putting the value of this cos theta here. So this is the value of cos theta, and putting it here, multiplying the two, we can rewrite the formula as, this remains the same, 2 1 by 4 pi epsilon naught QL. This becomes 3 here, 3 under root R square plus L square, or we can write 3 by 2 in like this. Okay. Then we can write 2QL as P in the terms of dipole momentum. And here L is very small. So we can ignore this, and this formula can be rewritten as 1 by 4 pi epsilon naught P by R cube. We take the ratio of electric field at the axial and the transversal line. It will be 2:1, or we can say E axial is equal to 2 times of electric field at the transversal line. So these are the two cases that we have discussed. Coming on to the third case. In this third case, the derivation when electric field is on a general point. This is the dipole, and any general point this has been kept. The electric dipole is a pair of equal and opposite charges separated by a small distance. This you know. Let us consider a dipole at point A and B. The dipole moment for this dipole is in the direction P. The dipole moment direction is P along the axis. Since dipole moment is a vector quantity, so P will have two components, P sine theta and P cos theta. So we are calculating electric field at point M. This is M, so we are trying to calculate the field at this point, which is a general point. If we extend P cos theta all the way up to the point M, then we can consider this as the axial line. We will consider this as the axial line. And now when we draw perpendicular from here, we draw perpendicular at M. This is actually parallel to P sine theta. The two formulas that we have just derived for the test charge at the axial and transversal line will be used again to calculate the resultant electric field at point M. If we add them up, we will get P vector of dipole. By vector addition, E resultant will be root A square plus B square cos theta. So we can say resultant will be E transversal plus E axial under root. So here putting the formula that we have just derived in the last slide. So 1 by 4 pi epsilon naught P sine theta by R cube whole square and 1 by 4 pi epsilon naught 2P cos theta by R cube whole square. Okay. We get the formula by solving this. We get the formula as taking 1 by 4 pi epsilon naught outside, P sine square theta plus 4 cos square theta by R cube. By trigonometry, we know sine square theta plus cos square theta equals to 1. So taking out of these 4, we take out 1 cos square theta. So we can rewrite this as 1 plus 3 cos square theta by R cube. In the next slide, we'll be covering up the relationship between this alpha and this angle theta. The general direction for angle alpha with vector r. Now, tan alpha is equal to perpendicular by base. Okay, so perpendicular is the equatorial and the axial. Putting the two formulas here that we have just derived previously, P r cube sine theta by P, 2P cos theta by r cube. 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught gets cancelled. Sine theta by 2 sine theta can be written as Sin theta by cos theta is tan theta, right? So it can be written as tan alpha is equal to half tan theta. That's the relationship between the two. Okay. Now, we are going to study the net force, torque and work done by a dipole kept in a uniform electric field. So let us understand uniform electric field here first. It is a field at which the magnitude of electric field is same at all the points. With the help of the external charge, say Q, an electric field is developed, and here the blue lines are indicating the uniform electric field. Now a dipole is placed in the electric field. Let us look at the animation now. This is the dipole and let us look at the animation now here. Okay. So however, what we have observed through the net force on the dipole is 0 since E is uniform. However, the charge are separated, so the force acts at different points, resulting a torque on the dipole. So when this is a uniform electric field, when they are coming, there is a torque which is developed because of the force in the opposite direction, and this angle is theta. Okay, and the formula for torque is force into distance. Force into distance. What is the distance here? Distance is BC. So this is the distance. BC is the distance. Okay. In terms of theta, we can say sine theta equals to BC by 2L. BC by the distance 2L. So here BC can be written as 2L sine theta. BC can be written as 2L sine theta. The value of force is that we know charge into electric field, charge into electric field. Okay, so that's the value of the force. Distance we have calculated 2L sine theta, so we'll put that value. So we have derived a formula, this QE into 2L sine theta, bringing down together 2QL. We can rewrite this as momentum, dipole momentum. So we can replace it with P. So P is sine theta. So I hope this is clear to you. And coming on to the next one now, the work done. So what is the general formula for work done? Work done is force into the distance, right? So force here we are going to take as torque and the distance is 2 theta. The formula for force, the torque we have just derived, PE sine theta into d theta. Putting up the limits 0 to theta and adding up the values, we can write work done is equal to PE 1 minus cos theta. These are all the formulas that we have derived in this video. I hope you can pause this and note these down. It will be helpful for you. Thank you.